Hello and welcome to today's video. In this video, we're going to talk about differentiation and derivatives. Now, you will remember that we've talked about continuity before, and continuity kind of describes the property of a function to be consistent with local behavior, meaning local behavior of a function around a certain point predicts the function value at that point through the limit. And if a function is continuous, then the function value actually is consistent with that limit. So that gives us a little information about the function. However, to really work with functions and know about their local properties, we will need some more information usually. And one possibility to get that information is differentiation. The idea is to analyze the local behavior of a function through approximating the function by a similar, locally similar, but very simple function. And the most simple functions that one could think of are constant functions or affine linear functions. The idea is to approximate a function through an affine linear function locally. Important parameters of that function. The most important parameter of that function is, of course, its slope. And that is exactly what the derivative of a function will tell us. It lets us know about the slope of a function at a certain coordinate, at a certain point of that function. So again, this section is called differentiability and derivatives. And the idea is a local analysis through approximation by an affine linear function. So what we want to do is we want to analyze the local behavior of a function through an approximation by an affine linear function. Now, before we define that more precisely, let me make a quick sketch to illustrate that idea. So here's a coordinate system. And let's say we have a function f, and the graph of f looks like that. So this is our function f. And we want to locally approximate that function. So let's say we have a certain point, we call that x star. We want to analyze the behavior of that function around x star. And what we can do is, we can of course compute the function value at that point first. So that's one important parameter. And then we can try to find a local approximation. So what we want is a tangent at that point to the function graph. So the local approximation would be a function that looks like this. All right, so this here is a local approximation through an affine linear function of f at the point x star. So you can see at x star, the function values of the function and the approximation coincide. And around x star, so as long as we stay close to x star, the function that approximates f and f itself are pretty close. And of course, as we move further away from x star, for example, here, the difference grows larger. But that is to be expected. So what do we need to construct this local approximation? basically two parts of information. The first is, of course, that function value here to get this precise point. And the second is we want to have the slope of that function. So to get the slope of a function, what we will do is we have to know about the ratio of the difference in x coordinates and the difference in y coordinates. So the slope of the approximation would be delta y divided by delta x. So we choose delta x arbitrarily, we compute the corresponding delta y, and that's the slope that we get. And of course, for each choice of delta x, the other slope would be the same here. Now the question is, how do we compute that slope from the function itself? And the idea of differentiation is to approximate that and then make the approximation better and better using a limit process. So what we'll do is the following. We'll take this point here and we'll take some other point that is also on the graph of f. Then we can connect those 2 points. And this forms a triangle. Right? The straight line connecting those 2 points. And the x part and the y part of that triangle. This gives us an approximation of the slope of f. Right? If we just use this as our delta y and this as our delta x. And you can see, of course, the slope of this line is not quite the same as the slope of this one. But as we move that point here closer towards this point, the approximation will get better and better. So we'll be closer and closer to the actual approximation, the actual orange line at that point. And we do this using a limit process. So basically we take the limit of the slopes that we get from this red function here as this point approaches x star. And that slope will then be called the derivative of the function f at the point x star. And using that derivative and of course the actual function value, we can then later construct the local approximation that we want. So here's the precise definition. To be able to do this, what we need is basically a function defined on an interval, and we want that interval to be open just to avoid complications with points on the boundary. Of course, we could resort to one-sided limits for the boundary points once again, but we would rather like to avoid that, to not have to discuss one-sided derivatives and things like that. One can do that, and it's totally fine to do that, but I'd like to avoid these technical difficulties for now. So we just assume that we have a function defined on an open interval. Let I be a subset of R, and let that be an open interval, meaning both boundary points are not included. And let f be a function on that interval. Then, first part of the definition, we'd say that the function f is differentiable at a certain point x star in this interval if the limit of these slopes exists. And I'll give you that limit in a second. So the function f is called differentiable at a point x star in the interval I if the following limit exists, and that is, I already said, what we do is we choose some point x and we move it closer and closer towards x star. So that's what's happening here. We take the limit as x tends to x star, and what we do is we compute the slope given by that red triangle here. So what we do is we compute this as delta y, and as you can see, the value here is f at the point x star. The value here is f at the point x. So this here would be the point x in our limit, and that moves towards x star. So this difference here, that difference, that is exactly f of x minus f of x star, right? And of course, this difference here, that's easy, that is x minus x star. And this is how we will compute the slope of that red function. So we compute f of x minus f of x star and divide that by x minus x star. And then again, we move the point x closer and closer to x star to approximate the slope of the orange function. So we call the function f differentiable at x star if this limit actually exists. And if this is the case, the limit itself, the value of the limit, is called the derivative of f at x star. So in this case, the value of this limit is called derivative of f at x star. And it will be denoted by the simple notation f prime of x star. Now there's a bunch of alternative notations. Some of those will be used in this lecture. Some of those you will encounter in the literature or maybe in other lectures. So just as a very brief overview of those, sometimes instead of f prime, people also write f dot. You'll often encounter that in physics or in engineering. Then there's also the more formal notation that we'll use sometimes. D over dx, meaning the derivative with respect to x of f at the point x star is written like this. And of course, there's all kinds of variations on that last notation. You can also write that as df dx at the point x star, means the very same thing. Or you could write this as df x star over dx. All of these mean the same thing, the derivative of f at the point x star. And just for the sake of completeness, this quotient here also has a name that is called the difference quotient. So the term f of x minus f of x star divided by x minus x star is referred to as the so-called difference quotient. So now we have defined what it means for a function to be differentiable at a certain point. And you remember we did the same thing for continuity. We defined what it means for a function to be continuous at a certain point, and then we extended that to the interval by simply saying a function is continuous on an interval if it's continuous in every point. And we can do the same thing for differentiability by just saying, well, a function is differentiable on an interval or any set if it's differentiable for each point in that interval. So the function f is called differentiable or differentiable on I. So often you just call a function differentiable to indicate that it is differentiable on its whole domain. If you mean a set other than the domain, you would have to add that to the name. So we call it differentiable on some subset. Okay, so the function is called differentiable on I, or just differentiable if it is differentiable at each point x star in I. And if that is the case, one can define a function that assigns to every point in that interval the value of the derivative, and that function is also called the derivative of f. So the function, again, that is denoted as f prime and is now regarded as a function on I that assigns a real number to every point in I, and is defined as x maps to the value of f prime at the point x. So this is then called, again, the derivative of f on I. And as I mentioned already, analogously, one can define one-sided derivatives. So let me just mention that those exist. So that's the last point of the definition. Analogously, one-sided derivatives can be defined using the one-sided limits, and then you just use the limits. X could tend to x star from above, and the difference quotient is of course the same. Like this, and x could tend to x star from below, and again the difference quotient is the same. And of course, if a function is differentiable, then these one-sided limits will agree and exist at the given point x star. But they would make a difference if you would consider boundary points of an interval, for example, where you can only take a one-sided limit. Well, there may also be functions that are not actually differentiable, but that may have one-sided derivatives at a certain point. So this is the formal definition. Let's look at a few examples to give us a toolkit of differentiable functions and their derivatives. So we'll start with a very simple example. Let's say we have a function f of x of the form alpha times x plus beta. So this is an affine linear function. Alpha and beta are parameters, real numbers. And of course, if the idea holds out, so if you want to approximate an affine linear function through an affine linear function, the result should be that very same function. So the slope that we would expect to get is exactly that parameter alpha here. And now hopefully our definition will provide that. So let's see if that actually works in the way that we intend it to. Now for x star in R, to take that limit, it's sometimes convenient to write x in the form x star plus h for some small value of h. So the idea is then to have that limit as x tends to x star of the difference quotient. Let me write it down first. So this could also be expressed as the limit of, well, instead of x, we now simply write x star plus h. So x is x star plus or minus, h could also be negative, plus or minus some h, minus f of x star. And of course, for x, we also write x star plus h minus x star. So one could express this limit here in this way. And then x tends to x star is the same thing as h tends to 0. So this is the limit as h tends to 0. And remember, that means that h could also take on negative values, right? So sometimes this expression makes it simpler to actually compute the derivative, and that's why I'd like to introduce that idea now. We'll use that frequently later on. So this is actually the same thing as the limit. Well, the denominator here is actually x star minus x star plus h, so what remains is h. And that means we have 1 over h times the numerator. Numerator is this one here. So let's take the function definition and substitute the x values here into that definition. And what we get is alpha x star plus h plus beta. So this is f of x star plus h here. And then we subtract f of x star, and f of x star is simply alpha x star plus beta. So this here is the f of x star part. And as you can see, what happens is something cancel out. So what we get here is beta plus beta, and here is a minus beta, so the beta cancels out. Here we have an alpha x star, and here we have minus alpha x star, so that cancels out as well. What is left is alpha h. So we're left with alpha h here. And of course now this h and this h also cancel out. So what we are left with in our final limit is just the alpha. Limit of alpha as h goes to 0 is not dependent on h anymore. So of course that limit is alpha. And that's exactly what we expected. So thankfully our definition seems to make sense. So that means f prime of x for affine linear functions is simply the alpha, meaning this derivative is constant. And of course, that's exactly what we expected. So let's turn our attention to another example here. Now that we've mastered affine linear functions and their derivatives, the next complicated step would be to have a look at monomials of the form x maps to x to the n for some n in n. In case n equals 0 and n equals 1, those would be affine linear functions, so we got that covered. But what about general n, higher n? Now let's see if we can say something about that. We'll do that employing a trick that we've used before. So again, we'll take the limit here of the difference quotient as x tends to x star. And of course, we can just substitute the function here. So what we get is limit as x tends to x star. We'll not use any tricks right now. So f of x is just x to the n. F of x star is x star to the n. And of course, we divide that by x minus x star. Another trick that we're going to use is we're going to factor out this factor out of this expression here. So what we will get is the following limit. Now we want to factor out x minus x star here in the numerator. And if we do that, what remains is, let's see, we need x to the power of n minus 1. So this times this is x to the n. That's exactly what we need here. And now if we multiply this by this, we get minus x star times x to the n minus 1. To make up for that, the second factor in our expression here will be x to the power of n minus 1 times x star. And if we multiply this by this, we get x to the n minus 1 times x star. So that's exactly the same thing as here, with the exception of the sign, right? We have a plus and a minus. So these two will cancel out. What remains is minus x star times this expression. That's x to the n minus 2 times x star squared. So you can see the powers of x decrease, the powers of x star increase in this expression. And we continue in the same way until we arrive at the expression x times x star to the n minus 2. And then the last expression that we get is x star to the power of n minus 1. And if we multiply this here, right, x star to the n minus 1 by x, we get exactly, we get x times x star to the power of n minus 1. And this is exactly countered by this times minus x star. So again, these cancel out. The last thing that is left is this expression times minus x star, and this gives us exactly this term here. So if you just try to compute the result of this multiplication, you will hopefully find that it gives you exactly the right expression here. So this is how you factor out this x minus x star. And now, of course, that factor cancels out. So that was the whole idea here. So what we get is, again, the limit as x tends to x star. And now we're left with x to the power of n minus 1 plus x to the power of n minus 2 times x star plus and so on up to x star to the power of n minus 1. Now what we have here is exactly n factors, right? N summons in that sum. And if we just substitute x star for each occurrence of x, right? If we take that limit here, then we get x star to the power of n minus 1 here. x star to the power of n minus 2 times x star. So again, x star to the power of n minus 1. And the same thing happens for all these factors until this one. That's also x star to the power of n minus 1. So all these factors will be equal to x star to the power of n minus 1 in the limit. And that means this limit is exactly n times x star to the power of n minus 1. And that is the derivative. So this limit does exist, and here we have the value of the derivative. So f prime of x for a function of the form x to the power of n is n times x to the power of n minus 1. So that's easy to remember. You just take this power here, write it in front of the expression, and then decrease this exponent by 1. So this already gives us quite some functions to work with. We have monomials, we have affine linear functions. Let's tackle a more complicated function as well. Let's tackle a square root. So the square root is a function that's defined on the non-negative numbers and maps to the non-negative numbers. And it's defined as f of x equals the square root of x. And again, we'll try to obtain the derivative of that. And again, we need a little trick. That's why I chose to show you this function here. We'll use, for the formulation, we'll again use x equals x star plus h. And we'll obtain the limit as x tends to x star of f of x minus f of x star divided by x minus x star is the limit as h tends to 0 of f of x star plus h minus f of x star divided by h. You remember that from our first example. And this is the limit as h tends to 0, 1 over h. And let's use the function definition. F of x star plus h is the square root of x star plus h. And f of x star, this one here, is the square root of x star. Now, to be able to compute that limit, we'd like to get rid of that square root expression somehow. And maybe you remember that from our discussion of sequences already, or limits of functions. We used similar tricks. What we'll do is we'll extend that whole expression by an appropriate term. And that term is the following. Let's again take the original first. So here we have a difference of two square roots. And we'll now extend that. We multiply that by the same expression, but we'll replace the minus sign by a plus sign. So here's a plus sign. And of course, we also have to divide by that expression. So in effect, we multiply this whole thing by 1. And you'll hopefully remember why we did this. We did this because we can apply the binomial formula to this expression here. And that will yield this expression squared minus this expression squared. And of course, that squares will get rid of these square roots. So that's the whole point behind this manipulation. So what we obtain is, again, that same limit here. And now we have square root of x star plus h squared. So that's just x star plus h. Minus the square root of x star squared. And that's just x star. So this is the new numerator. And for the denominator, we just copy the old expression. and hope that it won't make us any trouble. And well, as it turns out, x star cancels out here. This whole thing reduces to h, and we also have an h here, so those cancel out. And that, of course, makes the limit much nicer. So what we end up with here is the limit of 1 over the square root of x star plus h plus the square root of x star. And now as as h goes to 0, this expression here goes to the square root of x star. This expression doesn't have an h, so it's not changed. So what we have for the limit is 1 over the square root of x star plus the square root of x star. So 1 over 2 square root of x star. And that again shows the limit does exist, and the value is also given. So the derivative of f is 1 over 2 times the square root of x. Or, in other words, you could also write this as 1/2 x to the power of minus 1 over 2. And now if you remember that the square root of x can also be written as x to the power of 1 over 2, you'll see this is in line with the rule that we derived before. What you do to get the derivative is you just take this exponent, you write it in front of the function, like here, and you reduce the exponent by 1, and 1/2 minus 1 is minus 1/2. So you can apply the same rule to square roots if you want, or you can just adhere to this. Doesn't really matter, but still works. Finally, let's conclude with one more example. One example that shows you that not every function is differentiable, not even if it's continuous. And the most prominent example of this is this function here, the absolute value of x. Of course, you know how that looks like. So if I were to sketch the absolute value function, what you get is a function that looks like this. So this is obviously a continuous function. But I'm going to show that it's not differentiable at the point x star equals 0. So this point here is critical. And you want to see if there's a derivative at 0. So what we need to do is we need to compute the limit as x tends to 0 of f of x minus f of 0. So x star is 0 divided by x minus 0. And well, f of x is the absolute value of x. F of 0 is just 0, and that is divided by x. So this is the limit that we want to compute. And what we can now easily do is, to get rid of the absolute value, we can compute the one-sided limits separately and then see if they coincide. And if we do this, let's start with the limit from below. If the limit is taken from below 0, then that means we're only considering sequences where x is negative, below 0. So the absolute value of x for negative values of x is then the same thing as minus x. So that's what we can do here. We can just substitute that absolute value by minus x. And now the x cancels out. So we're left with minus 1 over 1, or just minus 1. And of course, that's then also the limit. And that is consistent with the graph here. So if we're in this area here, and you can see that function has a constant slope of minus 1. So you would expect that as the derivative, as long as you're not at the point 0. Now, if we're approaching x to 0 from above, Then with a similar argument, we can say that x is always positive, or at least non-negative. So that means the absolute value of x is just x itself. So what we get now is x divided by x. Again, x cancels out and we're left with plus 1 this time. So the one-sided limits do exist, but they do not agree. And that means the limit of absolute value of x over x for x to 0 does not exist. And that in turn means the function f is not differentiable at the point x star equals 0. So in particular, there are continuous functions that are not differentiable, at least not for all points. There are even examples for functions that are continuous everywhere but differentiable nowhere. The construction of these functions is fairly involved, so we're not going to discuss an example like that. But just as a word of warning, continuity is not sufficient for differentiability. As it turns out, however, the reverse is true. And let's also quickly write that down as the last part of this video here. So let I, a subset of R, be an open interval. And let f I to R be a function that is differentiable on I. And then the theorem says then f is also continuous. And one can prove that by simply, more or less simply, deriving the limit of f at a certain point through the difference quotient, basically through the local approximation through an affine linear function. That's just a technicality, more or less. I'm not going to go into the details here, but that's not a complicated proof. So a function that is differentiable is always continuous, but the reverse is not true. A function that is continuous may not be differentiable at certain points or maybe even nowhere. So please be aware of that. Continuity is not sufficient for differentiability. So this concludes this introduction into differentiability and derivatives. And in the following videos, we're going to talk about rules for differentiation to extend our portfolio of derivatives and differentiable functions a little bit. And as usual, I'll see you then.